All right, next video here. By the way, this is Professor Dan Kernler again with our Calc 3 series. Next video, we're going to talk about the gradient. We're going to define what the gradient is and then do a quick example. So the definition here, we're going to suppose we have a function z where both partial derivatives exist. The gradient denoted by kind of a little upside down delta. It's a vector. It is the vector whose components are the two partial derivatives. And there are going to be some very interesting and useful properties of the gradient that we will see in a little bit. First of all, to be clear, the gradient is not a directional derivative. Directional derivative is the slope of the tangent line in that direction, right? So the gradient is a vector. This is really important. So it's a function of two variables, which means it's two-dimensional and it lies in the xy plane. And one interesting way to think about the directional derivative, yes, it is then if we have the gradient, let me back up. One interesting use then of the directional derivative is we can, one interesting application of the gradient is we can reflect again and look back at the directional derivative. Remember that's the partial derivative with respect to x times cosine theta plus the partial derivative with respect to y times sine theta. Well, that would be the same thing as taking our gradient and then taking the dot product with our u vector. So in other words, the directional derivative is the gradient vector dot product with the directional vector. All right, so let's do an example. We are going to find the gradient of this particular function and then evaluate the gradient at a specific point. So that's easy enough. Find the derivative with respect to x. Y is a constant. Derivative of natural log of x is 1 over x. We're taking the derivative with respect to x. Y squared is a constant, so we'll just have y squared. And then the partial derivative with respect to y, natural log of x will be a constant. And then the partial derivative there, 2xy. Okay, so the gradient vector at any xy will be y over x plus y squared. And then for the y component, natural log of x plus 2xy. And if we find the gradient at the point 1, 2, we will get 2 over 1 plus 2 squared. Natural log of 1 plus 2 times 1 times 2. Oh, accidentally did erase, but now I need to do the erase on purpose. Oh, that's so cool. I am learning all kinds of new technology here. So we get the vector 6, 4. All right. Let's pop over to a maple graphic I made. So here is, the blue here is a graph of that specific function. And then, if we look from the top, we have that point. You'll notice where the point is there at 1, 2. And then here is the gradient. And so we'll kind of come back to this. There's something interesting about the direction that that gradient is pointing. So we will come back to that. Okay, so gradient, pretty straightforward. The two partial derivatives, and it gives you a vector, a 2D vector in a specific, in the xy plane. So next, a theorem with some properties. First, if the gradient is equal to the 0 vector. So if the gradient is equal to the 0 vector, then the directional derivative will be 0 in every direction. So what that means is if the directional derivative is 0 in every direction, right? Think about that. How could the directional derivative, how could the slope be 0 in every direction? Well, that's like at a peak of a mountain or at the bottom, like think of the bottom of a bowl or something. I should have a physical thing here since I'm talking about stuff. You know what? Let me go find something. All right. Couldn't find anything cool, but I did find this ratty old football of my boys in the basement. So if we think about a football sitting vertically here, where's the directional derivative 0 in every direction? That's right at the top. No matter what direction, the directional derivative is 0. It's like a little kind of parabolic there. And so the directional derivative is 0 no matter what direction we're traveling. Same thing on the bottom. So same thing there. So, all right, football. All right, so that is that part of the theorem. Next one, this is kind of interesting. We're going to investigate this and prove it in a second. The direction of maximum increase of the function. So we have a function of two variables. It's a z. The direction where the height is changing the quickest is the gradient. And also, the maximum value then would be the magnitude, the maximum value of the directional derivative. Would be the magnitude of the gradient, and then the direction of minimum increase or maximum decrease, if it's negative, is given by the opposite of the gradient. And the minimum value then is the opposite value of the magnitude. The minimum value, again, of the directional derivative is the opposite of the magnitude of the gradient. So the proof of 1 is very quick if the gradient is equal to 0, the 0 vector, I should say. Well, the directional derivative is the gradient, the dot product of the gradient with the directional vector. But if the gradient is the 0 vector, you have the 0 vector dot, the dot product with the directional vector, and that's going to be 0 for all u. So, end of proof. So if the gradient is 0, then the slope in every direction is 0. Proof of number 2 and number 3, a little more to this one. Let's let phi be the angle between a directional vector and the gradient. Okay, so phi is the angle between the directional vector and the gradient. We know that the directional derivative is the dot product of the gradient with the directional vector. And from our dot product, we know that this is the magnitude of the first vector multiplied by the magnitude of the second vector multiplied by the cosine of the angle between them. Now, here, let's use our fancy technology. Well, I don't know, fancy, whatever. We'll get a little color in here. So u there is a unit vector, right? It's our directional vector. How am I recording that again? Oh well. U is our directional vector, and so its magnitude is 1, and so we get then is the magnitude of the gradient times cosine of the angle between. Cosine of the angle between our directional vector and the gradient. And so what we have is the directional derivative, and we have a function for the directional derivative. It is a function of the angle between the directional vector and the gradient. And so we're wondering is, okay, for what angles phi is this maximum or minimum? So we have the magnitude of the gradient, which is just a known quantity. And so the directional derivative is going to be maximum when the cosine of phi is maximum. Now phi here, if we're looking at the angle between the directional vector and the gradient, let's just consider phi to be between 0 and pi. And so when is cosine maximum? cosine phi is maximum in that interval when phi is equal to 0. And in that case, so it's maximum when phi is 0. What that means then, in other words, then that the direction is actually, the directional vector is actually parallel to the gradient. So what this says is that the directional derivative is maximum when your direction is in the same direction as your gradient. In other words, the directional derivative is maximum in the direction of the gradient. And then the minimum value is a minimum when phi is equal to pi, of course, because then cosine phi would be -1 and you'd get the opposite of that. And in that case, u is parallel to the gradient, but in the opposite direction. So this is really important if we want to know which direction is going to be like the steepest incline. The steepest incline from a specific point is going to be the gradient of that surface. In fact, we can see that on our maple. You can kind of see here that if we go straight up the hill, that's the direction that, so this red here is the gradient. That's the direction that the gradient is pointing, is straight up that hill. And that's what it is. So if you're looking for, if you're standing on the side of a slope and you have this function z, which direction will be the steepest? Well, that's straight up the hill. That's the gradient. Which way will water flow? Well, water is going to flow in the steepest downward direction, so that will be the opposite of the gradient. So that is a really helpful property of the gradient. Yep, we're going to stop right here. That's it for this video. We have one more video from 15.5. We'll talk about a couple of other key properties of the gradient vector.